So now we're going to discuss call context sensitivity, or just context sensitivity for short, as it is usually referred to in the context of points to analysis. So the problem is explained by this example where there is interference of arguments across call sites. So let's say I use some kind of points to analysis. It could be Anderson's algorithm, Steengaard's algorithm, or some other algorithm. All these algorithms basically require you to transfer across different statements. And one type of statement is going to be a function call. So when there is a function call, let's say a call, using a function bar or baz, from bar there's a call to foo, and maybe there are two calls to foo from bar, and there's another call to foo from baz. Then there will be some arguments to this function, and then there will be some return values to this function that are returned by this function. And the function itself will have some function body. And when we do our points to analysis, then we are going to do our points to analysis on the function foo. By assuming certain initial values, initial points to values for x, for example, what can x point to? And depending on that, the variables in the body of function foo can point to some of the abstract objects, and eventually some value gets returned, which is also going to point to some abstract objects. Now, this transfer from the call site to the function involves copying the actual argument, in this case p1, to the formal argument, in this case x. So this function called dispatch involves a copy of p1 to x. And the transfer function, the corresponding transfer function, is basically the same as the copy rule, which is, you just take one variable y and assign it to another variable x, y equals x. So this is as good as saying x equals p1. So when you make the function call, when there's a dispatch, then you copy each argument from the actual argument to the formal argument. So this is equivalent to saying x equals p1 in this example. And then when you return, then whatever is the return value, so let's say the return value is y, that gets copied to whatever the return value in the calls at the call site is, in this case q1. So on return, the effective transfer function, or the effective logic that needs to be transferred across, is q1 equals the return value. So if it was y, then q1 equals y. Similarly, at this call site, you will first do x equals p2, and then transfer control to foo, execute foo, and then when you return, then you're going to do q2 equals the return value, and so on. So when I have to, so this was the actual execution, but when I'm doing, when I'm interpreting it for the points to analysis, or when I'm running a data flow analysis, then when I do an inter-procedural data flow analysis, so far we have usually been talking about data flow analysis in an intra-procedural setting within a procedure, but now you can also extend the same idea to inter-procedural. So when you do an inter-procedural analysis, whatever P1 could have pointed to based on your analysis in bar, that now X can point to, because as we already said, that the dispatch involves a copy of the actual argument to the formal argument. So whatever P1 can point to is now X can point to by the virtue of the transfer function for a copy statement. Now, again, this will be a weak update, because whatever X was pointing to originally, that remains. In addition, whatever P1 was pointing to, X now starts pointing to that. Recall that the transfer functions for all these statements, including the copy statement, was a weak update. Now, based on that, we get some points to set for X. Using that, we develop foo's points to graph, and we return the points to, we return a value. So whatever is the points to set of that value, let's say we return y, and so whatever is the points to set of y based on foo's points to graph, that gets copied to q1. Now the problem with this whole setup in this inter-procedural setting of points to analysis, which is very much required when we are doing points to analysis of any precision. Of course, one idea is to just use intra-procedural points to analysis, but that loses a lot of imprecision, because you have to conservatively assume that the arguments may point to anything and the return values may point to anything, and that really makes the precision very low. So if you want to improve the precision, then you do this inter-procedural copy of arguments and return values during dispatch and return. The problem, however, is that because there is a single points to graph, for foo, there's interference of arguments across call sites. So for example, let's look at Q2, then, because P1's value has been copied into X, then it will start appearing like Q2 can also access, can also point to anything that P1 could have pointed to if X was flowing into the return value. So let's see this with a more concrete example. So let's say, P1 was allocated at this location A1, at allocation site A1. P2 was allocated at allocation site A2. And let's say P3 was allocated at allocation site A3. Then by virtue of the function called dispatch at all these three places, it will appear that X can point to either A1 because of this call site and this dispatch, which is going to do the copy of P1 to X, or it can point to A2 because of this dispatch, or it can point to A3 because of this dispatch. Okay, and P1 can only point to A1, and P2 can only point to A2, and P3 can only point to A3. However, X can now point to any of these three. And now when I execute the points to analysis on the body of F, then I say y equals x plus 1. This is again looks like a copy, and then I return y. So this basically kind of gives me this relation, this points to graph for the body of foo, which says x or y and y could point to either A1 or A2 or A3. And then when I transfer this back on the return paths, then once again I have to copy y into Q1, and so that's a weak update on Q1 or Q2 or Q3, and so that basically gives me this points to graph, which is x, y, Q1, Q2, Q3. All of these variables can point to either A1 or A2 or A3, whereas P1 and P2 and P3 can only point to A1, their respective allocation sites, but it seems like Q1 can point to A3 or A2, whereas we can see clearly that Q1 can never point to A3 because Q1 can only point to A1 because P1 is flowing in, which is going to always have A1, and so we are missing the fact that this call here will only return here, but somehow our data flow analysis is also allowing paths like this where the return happens. You call at allocation at call site 1, but you return at call site 3, and that's just the nature of how this is the imprecision caused because of our static analysis. Okay, so what is the solution? Well, I think we have seen this before, and one of the solutions that we've discussed in the past is region-based analysis. The idea is that you summarize the whole procedure, in this case foo, and construct a summary transfer function for foo, and at every call site just invoke that summary transfer function. So that way these transfer functions, these summary transfer functions will be independent at each call site, and so there will be no interference. So let's see how that would work. Well, we're going to construct a summary transfer function for foo. And what should be the summary transfer function for foo? Well, in this example, the summary transfer function should just say that whatever x was pointing to, so x could have any arbitrary points to set, then y would have the same points to set, because it's just a copy. This plus 1 is just being treated as a copy here. And so y is just going to have the same points to set as x, and that's my summary transfer function. And then when I apply the summary across this call site, so that that transfer across this edge basically involves applying the summary transfer function. And because P1 can point to A1, so and the summary transfer function says that whatever P1 can point to, then Q1 that just we just apply the summary transfer function because we have summarized the function and not the we're not actually considering the values. So it looks like Q1 can only point to whatever P1 can point to, so Q1 can also point to only A1. Similarly, when I summarize the function foo, then I represent the transfer function as a whole single function and say whatever P2 can point to, then Q2 can point to the same thing, and so on. And that actually solves the problem for us and will give us a more precise points to graph. So instead of this points to graph here, I would just say that Q1 can point, so Q1 can point to A1, and Q2 can point to A2, and Q3 can point to A3. And indeed, the region-based analysis will solve the problem for us. However, this was a very simple example where the procedure body was really simple. But how do you decide what a summary transfer function should be if the procedure body has loops, etc., and complex control flow? Well, recall that there is one very easy choice of the summary transfer function, which is, whenever there's a transfer across a call site, just run the entire DFA fixed point algorithm on each transfer. So take the value at that call site, the argument values, and then just use those values and run those values through through a full DFA on the body of the callee. So in this case, foo. And this will be so at each call site, we may have a potentially different boundary condition, because depending on what the arguments are, what the points to set of the arguments are, that would define the boundary condition for that invocation of the DFA fixed point algorithm for the callee. And this basically means that if there are k call sites of foo, then there are at least k independent executions of DFA on foo. And if foo was a large function, then that multiplicative factor can become really prohibitive. Further, notice that I'm saying at least k, because actually you may require multiple transfers at each call site, because recall that the DFA algorithm is an iterative fixed point algorithm, and so that may require multiple transfers. And for each transfer, you'll have to run the entire DFA on the callee's body, on foo's body, with the new boundary condition. And so this is a problem. This is a scalability problem. This is a huge scalability problem, and this can be seen especially because the number of such invocations can grow exponentially with the call depth. So, example, if the main function calls b twice, then b's summary transfer function will be executed more than twice, as we saw earlier, because there are two call sites. And if b is calling c twice, then c's summary transfer function will be called at least more than 4 times, because b will be called twice completely independently with different boundary conditions, and each time b is called, c's will be called, and c will be called twice for each of them, and because these are completely independent, we are going to execute the c summary transfer function greater than or equal to 4 times, which may eventually call foo, and so foo's summary transfer function may get executed more than 8 times if foo was being called twice in C, and so on. So in general, the number of times you have to execute the DFA on the whole body of a function may be exponential in the call depth, and this is a huge scalability bottleneck. If you have programs that are thousands to millions of lines of code, then something like this will never scale. So to summarize, region-based analysis yields more precise solutions. In this example, these are the kind of solutions that we'll get, but it has exponential time complexity, and that's a deal breaker. So that's a good motivation for context-sensitive analysis, and the idea here is that we will still construct a separate points to graph. So instead of actually invoking and treating the whole callee's body or callee's transfer function as a function and completely re-executing it all the time, we are going to construct a separate points to graph of foo for each call context. So somewhere in the middle, so a completely context insensitive or the original analysis was basically just having a single points to graph for foo. The summary transfer function or the region-based analysis basically didn't have any points to graph or C. It will just recreate the whole points to graph at every call site. So that's almost like inlining the callee at every call site, and that's also super expensive. This is a middle path where you do a separate points to graph for each call context. So you define a set of call contexts that you are interested in, and then you have a separate points to graph for each call context. So for example, you could say that, and so how do you decide what the call contexts are going to be? So you have some finite small number, manageable number of call contexts. For example, you could have one depth call context, which means that I'm going to have one call context for every call site, and that's it. So if there is if the call chain has a depth 10, then I'm just going to look at the last call site and use that as a calling context. And so for all the above all the functions that are calling that call site, we're going to ignore that part of the call context. So they will all have the same common points to graph. So for example, in this case here, if for example I have a call context of depth 1, then foo will have only 2 call contexts, because foo has only 2 call sites, but at depth 1 of the call chain. And so irrespective of whether b called c here and then reached here, or whether b called c here and then reached here, we are going to have the same common points to graph. So this is an improvement, precision improvement over having a single points to graph for foo, instead of single points to graph, I have 2 points to graph now. So it's a better improvement. At the same time, it is not as expensive as a region-based analysis. You could have exponential growth in the analysis time. Now, how do you decide which call context and how many call contexts to have? So one common thing that has seemed to work most and people use a lot is using one depth call context. So have a different call context for every function at every call site. So for example, in this example here, there will be 2 call contexts for foo, there will be 2 call contexts for C, and there will be 2 call contexts for B. And well, I mean, of course, this is a heuristic, and there are practical trade-off considerations in making these such choices, but this is something that people commonly use. A more general approach could be to use k-depth call context, in which case, and you can do this, when you do this analysis, you can mix and match. You can say that for certain functions, you will use deeper call context depths while doing the call context sensitive analysis, points to analysis, and for other functions are you going to do shallower ones depending on the structure of the program. So this is the basic idea of context sensitivity, and we're going to look at it in more detail in the next module.